In today's Chem Help video, we're going to be examining the topic of buffers. It's a key component of the WACE exams and often one that's done poorly by students because they don't follow a standard model. So what we want to do is have a look at that concept and see if we can make it easy for you to always get success when answering these questions. So first of all, what are these things called buffers? So first of all, let's start off with a definition. A buffer is a solution that resists a change in pH when small amounts of acid or base are added. This is a question you might get asked in a test or an exam to provide that definition. So we don't do a lot of definitions in chemistry, but this is definitely one of them. Now the key to this sentence is that small amounts of acid and base are added. They're not superhuman sort of things. They can't resist all acid and base changes, but when a small amount of acid or base is added to the solution, essentially what happens is that pH will not change. Or if it does change, it only changes by a very, very small amount. How do you make a buffer? That's the next thing I often get asked. A buffer consists of a mixture of a weak acid and its conjugate base, often in as close to equimolar quantities as we can get, and thus has the capacity to react with both added acid, or hydronium, or base, or hydroxide ions. So the equimolar is quite important, and we'll come back to that later. Buffers are essentially artificially created equilibrium systems. Now there are some natural ones that get set up as well, so in some river systems for example, but ones we're going to use in the lab are artificially created ones, where the concentration of the weak acid on one side of the equation and its conjugate base on the other side are close to being equal. Now we know that in a real equilibrium that wouldn't be the case. Weak acids usually have small values of K, something like 2.4 times 10 to the minus 3 or less. So that would mean that there's lots more reactant, or that weak acid, and very little conjugate base. But a buffer is different. A buffer has almost equal. So if it did have a K and it doesn't, it would have a K close to 1, where both the reactants and the products are close to each other. So this is just a graphic demonstrating that. So you've got your weak acid, which is represented by the pink circles with a tiny blue dot on it, and the tiny blue dot of course represents the proton, or the H+, and A- is the weak base, or its conjugate base, and that's just the pink circle with a little minus symbol on it representing its negative charge. And you can see that in the buffer system you've got water, you've got the weak acid, and you've got the conjugate base. So how they work is that any added hydronium from an acid reacts with the conjugate base, forming more of the weak acid molecules, and that's represented in that equation above the box on the right. So when you make those weak acid molecules, they are an unionized particle, so they don't contribute much to the pH of the solution. So essentially what you're doing is you're neutralizing the acid by having the added acid react with the conjugate base. If you add hydroxide ions from any base, it reacts with the weak acid itself, forming more of the conjugate base. So what happens is the hydroxide ion takes the proton from the weak acid turns into the conjugate base, and the added hydroxide simply turns into water. So that means any added base essentially is neutralized. Now the thing about this is, because there's equimolar quantities, there's lots of weak acid, there's lots of conjugate base, it can react to both added acid or base, and that means that the net change in pH is negligible. That's why it says that the buffer can react to small additions of acid or base, leaving the pH the same. Buffer behavior can be viewed from the perspective of shifts in the position of this weak acid equilibrium, and collision theory can be applied to predict and explain the response of a system to an imposed change in the form of added acid or base. So what we're doing really is we're using our equilibrium topic and the way we'd answer questions using collision theory to predict and explain what's going to happen when acid or base is added. So what we're now doing is we're linking the equilibrium topic to the acids and bases topic. And this happens a lot throughout year 12. So we're going to give you an example. And this example is ethanoic acid and its conjugate base, ethanoate ions. One tip for you is that when we write these buffer questions, always write them as a hydrolysis equation, which essentially is where the weak acid reacts with the water, that's what hydrolysis is, to turn into hydronium and the conjugate base. If you write them in this model all the time, it makes it a lot easier than trying to do them conjugate base with a weak acid and a whole different other ways to write these equations. If you stick to this model, it always works every time. So, if we add acid, the concentration of the hydronium ions increase. That's what's going up with that orange arrow. So we're thinking about our equilibrium. Acid is going up. That causes more collisions between particles on the product side of the equation. Thus, the reverse rate of reaction will overtake the forward rate, which was unchanged initially. More reactants are formed, and the net result is that almost all of the added hydronium is consumed. The pH essentially remains constant. Now that's why, again, you need to have those high concentrations of both the weak acid and the conjugate base, and they need to be equimolar. So that's the thing about buffers as well. They're not like very, very dilute. Concentration is usually quite high. And we know that in equilibrium theory, we can never completely eliminate a change, but we're eliminating almost all of it by the reaction of the acid with the conjugate base. Equilibrium shifts that way, and the hydronium goes down. Also, of course, some of the conjugate base will be consumed as well. When we add base, what happens there? Now, if you look at that equation, you'll say, oh, but there's no base in that equation. So that's where we need to look at the hydroxide ions and what they'll do with the hydronium. So we know that the hydroxide will react with the hydronium and form water, so essentially neutralizing them. That lowers the concentration of hydronium ions in the system. Therefore, there's less collisions between particles on the product side of the reaction. Decreases the reverse rate. Forward rate, however, is completely unaffected because none of those particles were changed. Equilibrium shifts to the right. We replace the lost hydronium, and essentially the pH remains the same. So in both cases, added acid or base, what we're doing is we're playing with those hydronium ions, and that is why I ask you to write it as a hydrolysis equation, because we're constantly looking at the same particles changing, and then it's just about shifting. Now, the extent to which a buffer can resist changes in pH, of course, does depend on the amount or the concentration of the weak acid and its conjugate base in the system. If these components run out, then the buffer will no longer work. So that's kind of a definition that you need to know, which is called buffer capacity. The extent to which the buffer can resist changes in pH by absorbing the extra hydronium or hydroxide is known as the buffer capacity. That's another definition for you to know. Buffer capacity depends on two main factors. The first one is the relative concentrations of the weak acid and its conjugate base. The most effective buffers have an equal proportion of each. That's that equimolar thing I was telling you about before. So if you have equal molar concentrations on both sides, that's part of buffer capacity, and then the actual concentration of the weak acid and the conjugate base. So not only are they equal, but the higher the concentration they are, the more they can respond to the changes. If you think back to that definition of what a buffer was again, a buffer is a substance that resists change in pH when small amounts of acid and base are added. Now that small depends on the actual concentrations. If the actual concentrations are very low, then the small is very small. As the concentrations of each of those two things increase, then you can resist more. Now there are a lot of, I said before, that there are buffers are essentially artificially created, but there are biological ones as well that do exist in nature, and a large number of biochemical reactions taking place in living things only work within a very specific and narrow pH range. Biological reactions are catalyzed by complex proteins called enzymes, whose action is dependent on a region known as the acceptor site having a very specific shape. The acceptor site is where the molecules of specific types, called the substrates, are bound during a reaction mechanism. And the shapes of the proteins are determined by secondary intermolecular hydrogen bonding interactions between these long parts of amino acid polymers. And we will look at amino acid polymers and proteins later on in the organic chemistry section of the course. But essentially what happens is that if you have the pH change, the shape of the enzyme changes. And if you remember back to year 9 science, we talked about lock and key. And basically what happens is that if the pH is wrong, the shape changes and the key will no longer fit in the lock. It's a very simple way to explain it, but basically what that means is that the enzyme doesn't work anymore. And that can lead to serious illness or even death. And there are many buffers in the human body that stop that happening. One of those places is blood. Blood pH needs to be in a very narrow range, so 7.4 pH plus or minus 0.05. If the pH of the blood falls outside this range, it can affect the operation of the cell membranes, that's the outside of the cells, and prevents enzymes from functioning correctly, or again, as I mentioned earlier, alter the protein structure. A blood pH that would be 7.8 or lower than 6.8 can actually be fatal to a human. So, you don't want overly alkaline blood, which means basic, or overly acidic blood. And these are biological processes called acidosis and alkalosis that can link into that. But blood maintains the narrow pH range with the aid of carbonic acid. And it forms a carbonic acid hydrogen carbonate buffer system. And think about it this way, if you ingested some lemon juice, for example, you don't want to keel over because your blood becomes acidic all of a sudden. The blood needs to be able to absorb that change. In this particular buffer system, the weak acid, the carbonic acid, and the bicarbonate ion or hydrogen carbonate ion is the conjugate base. And remember, the difference between a weak acid and the conjugate base is simply one less hydrogen going from the weak acid to the conjugate base. That's how you match them up. So if we write our buffering equation in the model that I'd like you to use, which is the hydrolysis equation or the reaction with water, you can see that carbonic acid donates the proton to the water. So the water is acting as a Bronsted-Lowry base. You form hydrogen carbonate ions and hydronium ions. Buffers are also used to calibrate pH meters, because as you dip the pH meter in and out of different solutions, we want to make sure that that pH stays the same. So buffers are used for that. The pH value of a buffer system is really dependent on the Ka of the weak acid being used and the proportion of the acid molecule and conjugate base. The mathematics of all this is really quite complicated, and we could deal with it as an extension, but we'll come back to that later. Alright, so here's a couple of WACE style questions. The buffer question has been a fixture of most recent WACE papers, and they usually follow a standard model as shown in the next slide. As it says, they're generally not done well at all, and mastery of this style of question will give you an edge over other students who are trying to compete with you. So here's an example. Given this buffer system, okay, so we have that weak acid, H3C6H5O7. And as I said, put it into the hydrolysis equation with water and take one hydrogen off it and form the anion, which is the conjugate base, and hydronium ions. So the question is, explain why only a small change in pH is observed in this buffer solution when a small amount of sodium hydroxide solution is added, compared to adding a similar amount of sodium hydroxide solution to a system that's not a buffer, such as water. So what they're asking, they say if you add sodium hydroxide to the buffer, pH doesn't change. If you add sodium hydroxide to water, the pH does change. So why is that? How to answer. This is how you go about it. Use a really clear system. State what changes. Hydroxide ions added to the system are removed, neutralized by reaction with the hydronium, and show the equation. So that's your neutralization equation. And then show your buffer system. How does the equilibrium respond? This causes collisions between the products to decrease, and the reverse rate slows. The forward reaction overtakes the reverse, and more products are therefore produced. State what changes. The hydronium lost in a neutralization reaction is replaced, and there's negligible change in the pH. And this is the bit, fourth bit, is what is often missed in the WACE, contrast to the other system. Recognize that when OH is added to a non-buffer system, such as water, there is no weak acid species or conjugate base in there, so there's nothing for the added substance to react with. So the added hydroxide contributes fully to the pH change. So in this case, you'd need weak acid for the hydroxide to react with, and the non-buffer doesn't have it. Now in titrations, which we'll get to as part of our volumetric analysis section of the course, the titration curves for the neutralization of a weak acid with a strong base, you can see buffering there as well. When the number of moles of base, which is sodium hydroxide, equals half the total number of moles of the weak acid and its conjugate base are in equal amounts, and that's a buffer. So the ratio of weak acid to conjugate base is 1:1. As you've previously seen, this is the ideal setup for a buffer system, and the pH equals what's called the pKa. And this explains why there can be addition of a relatively large amount of base, but the pH doesn't rise until the equivalence point is close and the amount of acid has decreased to almost nothing, and therefore the solution is rich in that conjugate base. The buffer system has passed its capacity and is exhausted, and that's when you get that rapid change point. One way to make this buffer would be to use some weak acid, such as 320 mils of a 0.1 molar weak acid, and add it to 100 mils of a sodium salt of the conjugate base. That would give us 400 mils of a solution with a pH of 4.5. And here's a graph that shows you that little buffer zone. So what's going on there, you can see that between those two dotted lines, we've got actually the addition of quite a lot of solution. So it's over 20 mils were added. So 20 mils of sodium hydroxide being added, that's quite a lot. But you can see that the pH doesn't really change much. It's that sort of flat zone almost. And then as you get close to the equivalence point, we get a rapid change. So hopefully some of that information will help you when you're looking at buffers. But always, as always, if you have any questions, please post them and ask.